Hi, everyone. Welcome to our next video for week 7. We're going to talk about tests of significance. So the correlation coefficient R, which we talked about in our last video, is based on sample data. To decide whether that linear relationship in the sample data is strong enough to use to model the population as a whole, we're going to use a hypothesis test. This type of hypothesis test is called a test of significance of the correlation coefficient. We're going to use the same p-value method we've been using for all of our hypothesis tests over the last 2 weeks at this point, I think. So same 4 steps. We're going to review them here, and then we're going to talk about how to find that p-value method and do a couple examples. A note that this is a t-test. So we typically use a t-test for R values. So let's quickly review the p-value method. We state our hypotheses. In this case, there isn't any concern about identifying your claim. We're going to calculate the p-value. We're going to make our decision, just like we've done before, and then we're going to write a conclusion. So when we state our hypotheses for a test of significance, they're always the same. The assumption, that null hypothesis, is that the population correlation coefficient rho is equal to 0. So our base assumption is that there's no relationship between X and Y in the population. The alternative is then that the population correlation coefficient is not 0. There is some linear relationship between X and Y. In words, H naught is there is not a significant linear relationship between X and Y in the population. And the alternative is there is a significant linear relationship between X and Y in the population. To calculate the p-value, we're going to enter those X and Y values into list 1 and list 2. Ideally, you've already done that because you have found your correlation coefficient. And then instead of running option 8, lin reg a plus bx in the calc menu, we're going to go stats test, and we want lin reg t-test, linear regression t-test. It's option F. It's way down towards the bottom. It's going to ask you where your X values are, where your Y values are. Your frequency should be 1. And then you always want to select the not equal to 0 option. And it will output both a test statistic and a p-value. And just like all of the other tests on the TI-84, it will label the p-value as a lowercase p. Unfortunately for GeoGebra, they don't have a built-in linear regression t-test. So we're actually going to have to calculate that p-value a different way. So to calculate the p-value for a test of significance, first you have to find that test statistic. And the formula is your test statistic is your correlation coefficient R times the square root of n minus 2 over 1 minus R squared. And remember, you should already have R and R squared. That's something that you did before you're running a test of significance. And n is the number of ordered pairs that you have. So the number of rows in your data table. We're subtracting 2 because now this is a 2-variable problem. And so we're subtracting 2 from our degrees of freedom instead of 1. Then we're going to run t-distribution to figure out the area in the tail for our test statistic. That degrees of freedom is n minus 2, and the test statistic is what we just found. And give me just a second. I want to write that down so everybody remembers. If I could find my pen. So So our degrees of freedom is this right here. So that's going to go here. And then whatever you get as an answer, that's going to go here. So what this is doing is it's taking that t-distribution, which kind of looks like a standard normal. We know that this is 0. It's going to take whatever test statistic you feed it, and it's going to find the area to the left, which is our p-value. However, because GeoGebra by default finds area to the left, if your test statistic is positive, it's over here above 0, the computer is going to find this, which is not what we want. So after you've run the t-distribution, if you end up with a probability that's bigger than 0.5, do 1 minus that answer and use that as the p-value that the calculator spits out. There is one more step after you've found that probability or that area in the tail. You do need to double it. You have to multiply it by 2 because this is a two-tail test. Don't worry if that sounds a little scary. I'm going to work through this process with you in an example so you can see it from start to finish. Let's go ahead and do our first example. So example 12.6, random sample of 11 stat students produced the following data. X is the third exam score out of 80. Y is the final exam score out of 200. Perform a test of significance on the correlation coefficient found in the last video. So you can see here we have the R and R squared value that the calculator spit out with the hit. And we're going to go ahead and run a test of significance to see if this R value is strong enough to indicate that there's likely a linear relationship in the population and not just this random sample of 11 students. So I'm going to clear out this data to make room to work, and we're going to go ahead and do the 4 steps. So first step of our test of significance, we state our hypotheses. For a test of significance, which we're specifically told we're doing, I know it's rho equals 0 and rho does not equal 0. So no relationship in the population. And then this is, there is a relationship in the population. I'm going to erase that because it looks. Second step, we want our p-value. So we know that we're putting our x values into list 1, we're putting our y values into list 2, and then we are calling lin reg t test. And it asks us for list 1, list 2. It asks us for our frequency, which we know is always 1, and our tail, which is always not equal to. So let's go ahead and pull that TI-84 back up. And we're going to go stats, test, and then all the way to the bottom. And you can see that third from the bottom, lin reg t test. So data is in list 1 and list 2, frequency is 1, not equals. We can store the regression equation, but we typically don't. We've already done that at some point, and just straight to calculate. And you'll see it spits out a whole bunch of stuff. It spits out our assumption, and then it spits out a test statistic. So the test statistic is 2.6576, and it spits out our p-value, which is 0.0262 rounded. But you'll also notice it spits out some other stuff. We see that A and B for the regression equation, y equals a plus bx. We see an S value, which we haven't talked about, and then an R squared and an R. So you can, if you know that ultimately you need to do a linear reg t test, you can put your data in list 1 and list 2 and go straight to LinReg t-test, and it'll find everything you need in one go. So that is an option if you know you're going to have to do this whole process from start to finish. From here, we make a decision and we write our conclusion. So for 3, I know I need to compare my p-value to an alpha. And if we're not given an alpha, we assume 0.05, and 0.02 is less than 0.05. So that means we're rejecting our null. So we would say that there is a significant linear relationship between X and Y in the population. And you'll notice that's the statement from the previous slide about what that alternative hypothesis means. So in step 3, if we reject the null, then we're supporting the alternative. And my conclusion in step 4 is just a restatement of what that alternative hypothesis means, that there is a significant linear relationship here. Okay, so my hope is that process kind of feels familiar. Same 4 steps we've been doing for a few weeks. I want to try another example in GeoGebra. So for those of you using GeoGebra, you can see what that test statistic process looks like. So let's go back to our try it 12.6 from previous videos. So this is the scuba divers have maximum dive times they cannot exceed. Data on the right shows different depths with the maximum dive time in minutes. Perform a test of significance on the correlation coefficient found in the last video. So we have the correlation coefficient for this set of sample data. We know that R is negative 0.9629. So the sample is strongly correlated. We want to check that that correlation translates to the population as a whole. Is that statistically significant? So let's go ahead and pull up GeoGebra and check that we've got our data in there. So if I scroll back up, you can see that this data is ready to go. So I'm going to go ahead and clear that data table. We're going to start the process. And all tests of significance start the same. The null is that row equals 0. The alternative is that row is not equals to 0. 2 is where we find the p-value. And for GeoGebra, we start with that test statistic. So t is equal to r times the square root of n minus 2 over 1 minus r squared. So here our r is negative 0.9629. And then we have a square root. And then I'm going to, and it's going to be a little messy, bear with me, pop that data table up again. And count the number of rows. 1, 2, 3, 4, 5, 6. There's 6 rows of data. So n is 6. We have 6 ordered pairs. So 6 minus 2 all over 1 minus, and then we have our r squared from before, 0.927. So first thing, we're going to pull up GeoGebra. We're going to plug that formula in. So you can see the work there, and we get a negative test statistic, which makes sense because we have a negative R value out in front of that square root. So our test statistic is negative 5.1448. So we're going to go ahead and run that t-distribution call to get our p-value. And I'm actually going to do something because I want to be extra accurate. I know that I can call that value, that unrounded answer that I just got, because the calculator gave it a name. GeoGebra stored that value in the variable d. So when I call, maybe if my computer works, this distribution, it wants the degrees of freedom first. 6 minus 2 is 4. And then it wants that test statistic, which we saved as D. And you can see it spits out something that looks like a p-value, a decimal value, 0.0034 rounded. Step 3 and step 4 are the same. We're comparing that p-value to an alpha, a level of significance. Again, this word problem didn't mention one, so we're going to assume it's 0.05. And 0.003 is less than 0.05. So we're going to reject our null. So just like the last problem, we can say that there is a significant linear relationship between X and Y in the population. Oops. So based on this sample data from scuba divers, we can be fairly confident that there is a significant linear relationship between the dive depth and the maximum dive time. Specifically, because our R value is negative, we can be fairly confident that when the dive depth goes up, that maximum dive time is going to go down by a proportional amount. There is a linear relationship between those two things, and it's negative. So as one goes up, the other is going to go down. Okay, if you have any questions on how to carry out that hypothesis test, a test of significance, feel free to contact me via email or drop by office hours Monday, Thursday, or not Monday, sorry, Tuesday, Thursday, or Friday. Otherwise, I will see you in our next video.